Good evening, Bromsgrove. Yes, this is Gaia. As you can see from the top there, it had a 5-year mission to map 1 billion stars. It did that so well, they changed its mission to a 10-year mission to map 2 billion stars. So what I'm talking about this evening is I'm going to be covering why we want to map the Milky Way, how you can map the stars in the Milky Way, what type of data can you get, and what, at the end of the day, do we learn from all of the data that Gaia is producing. So you can start with why map the stars in the first place. In other words, you can ask the question, where are the stars? But then you can say, okay, we want to map the stars so that we know where they are and we can find them at a later time, or tell if something has moved, or tell if any new objects appear. But why do we need Gaia for that? All we need is a star atlas. We just look and those are the stars. Look, we can see them on the star atlas. So why do we need Gaia? Well, Gaia is not useful for making star atlases, but it is useful, it is absolutely necessary if we want to measure the positions of stars within the Milky Way, not simply where do they appear to be in our sky, but where are they actually in 3 dimensions and how are they moving to tell us about the evolution of the Milky Way, the dynamics of the Milky Way, and the history and possible future of the Milky Way galaxy. So how is it that we map the sky? Do we simply take a lot of images and stitch them together? That works fine. If you look down on the Earth, that's how Google Earth works. Take a lot of pictures, stitch them together, job's done. But one of the problems with doing that for the stars is that stars move. Everything in the galaxy is moving. Nothing in the galaxy is static. And therefore, we can't simply take a snapshot, stitch them together and say that is what the Milky Way looks like. And of course, there's a second problem, and that is even if we could just photograph the entire sky, knowing where they are in 2 dimensions is not good enough. If you think about how we look at the Orion constellation, for instance, from Earth, we see it as a familiar pattern of stars, but when we think about the distances to the stars, well, they're not in any particular pattern at all. They're spread over deep space. The fact that they happen to line up in a patch of sky is purely coincidental. So the only way we're going to get the full picture of where the stars are in the Milky Way is to look at where they appear to be and to get their distance. Distance is absolutely critical if we want to understand the structure of the Milky Way. Actually, it's quite important if we simply want to understand the stars themselves. Because if we think of the familiar plot of luminosity on the vertical scale and color on the horizontal scale, if we don't know the distance to a star, we can't tell if it's a very bright star fairly distant or a very dim star relatively close to us. We need to know the distance in order to know the luminosity. So in other words, we might be interested in a star that seems to have a surface temperature of 10,000 degrees, but that doesn't tell us whether it's a supergiant or a main sequence star or a white dwarf. And similarly, if we look at a star with a surface temperature of 3,000 Kelvin, well, we don't know if it's a supergiant, a red giant, or a red dwarf, unless we know its luminosity. Yes, we can get clues from its spectrum, but we essentially need to know the distance so that we can work out the luminosity so that we know what type of star we're dealing with. And as an aside, if we don't know the properties of a star, then we really don't know much about the exoplanets that might be going around it, because all of the techniques we use for finding exoplanets give us the mass of the planet relative to its host star, or the size of a planet relative to its host star. So if we don't know any of the properties of the host star, then really we don't know much about the exoplanets going around it either. So we really absolutely do want to know about distance. And that means we need to think about distance to the stars. That means parallax. This idea, perhaps you're familiar with the idea, that if you hold your finger up and blink your left and right eye, the finger appears to move against the backdrop of more distant objects. And it's often said that in order to get parallax, all you need to do is to think about the fact that a nearby star moves as the Earth goes around the sun, and hence as we see it from different viewpoints in the Earth's orbit around the sun, near stars seem to move against the backdrop of more distant fixed stars. But bear in mind, there's no such thing as a fixed star. All the stars are moving. So that diagram is rather simplistic in that sense. This is the angle we're interested in. For a given star at a given distance from this triangle, the more distant a star is, the smaller that angle is, because the distance from the Earth to the Sun, 1 astronomical unit, that's effectively a fixed baseline. And so more distant stars will have small parallax angles. If we think about the problem, yes, all stars appear to move, so that's why this diagram is a little bit misleading. It implies that if we have fixed stars in the background, we can simply line things up. It's never that simple. If we take a hypothetical, what if we had a star at a distance of 3 light years, then if we work out the maths of that triangle, 3 light years for the length of the triangle, 1 astronomical unit for the baseline, it turns out that parallax angle is 1 arc second. And the idea of a distance which gives you a parallax of 1 second, that's a parallax second or a parsec. So 1 parsec, when you do the maths, turns out to be 3.26 light years. But remember, all the stars are more distant than that. The closest star is 4 light years, and therefore all stars, because of the Earth's motion around the Sun, will appear to have a parallax that's less than 1 arc second. Remember, 1 arc second is about the best amount of detail you can ever expect to see in an amateur telescope. That's a sort of a yardstick for an arc second. Arc second being 1/60th of an arc minute, being 1/60th of a degree on the sky. So there's the crux of the problem. We absolutely need distances, both to understand stars and to understand how they are moving in a dynamic Milky Way of billions of stars. So we need parallax, but parallax needs to know the position of the star, not simply the position of one star relative to another, because if they're both moving, how do you actually know what's going on? So you don't simply need the position of a star relative to other stars, you need it relative to some fixed coordinate system. And you also have to take into account, not only will the stars appear to move because of the Earth's motion around the Sun, individual stars are moving around the center of the Milky Way. They have their own motion, so-called proper motion. So we've got a rather entangled situation of looking out into the Milky Way, seeing things move because we are moving on the Earth around the Sun, and we've got the stars themselves moving. That is why mapping the Milky Way is not a trivial task. The distances these things appear to move because of the Earth's motion or the actual motion of the stars is not a lot. We need very high precision to actually determine these motions, these apparent changes in the position on the sky. So, how can we map the sky accurately? This is a sort of cartoon, if you like, reminding us that when we look into the sky, this is either a patch of sky with exaggerated motion, or if you want to think of it as a small patch of sky. Individual stars are moving because of the Earth and moving in their own right. If I draw some imaginary fixed circles, you can see that stars are moving relative to each other. Some are moving quite slowly, some are moving quite quickly. We've got to untangle all of that motion to try and figure out what's actually going on. How can we tell which ones are actually moving if everything seems to be moving relative to everything else that's in the sky? So we need to untangle the two. In order to untangle the motion because of the Earth around the Sun, which we need to get the distance, as well as the motion of the stars, which we need to understand how the Milky Way is behaving, we need at the very least some really high precision measurements. And we also need a fixed coordinate system, because as I've said, knowing how one star is moving relative to another star is not helpful. We need to know how it's actually moving. So we need high precision and a fixed coordinate system. Very high precision because the angles we're talking about are tiny. Remember, no star has got a parallax angle as big as 1 arc second. At distances of hundreds of light years, the parallax angles we're talking about are going to be a tiny fraction of 1 arc second. And we need a fixed coordinate system so we can make sense of the apparent motion because of the motion of the Earth around the Sun and the actual motion of the stars themselves. As a bit of an aside, it was said in the 1980s, why don't we make this problem easier? If parallax is determined by the distance to the star and the baseline that we are changing to see the changing position of the stars, we can't make the stars any closer, but we could in principle make the baseline larger. Instead of having a baseline which is determined by the Earth's motion around the sun, why don't we take a spacecraft and send it to the edge of the solar system, 1,000 AU away, to give us a baseline 1,000 times bigger? That makes the parallax 1,000 times bigger and 1,000 times easier to measure. Well, this was seriously considered to take a spacecraft and fly it to the edge of the solar system. It was calculated it would take 50 years to get there. So if they actually went ahead with this plan in the 1980s, it still wouldn't be there yet. So they decided not to bother with that particular plan. They figured, let's make the measurements here on Earth as accurate as possible, or close to Earth as accurate as possible. Let's not think about making the baseline any larger. So what coordinate system do we use to map the stars? You might say, well, isn't that fairly straightforward? We know about coordinate systems. If we pick up an atlas, we know the positions of the stars on a coordinate system which is given by right ascension and declination. Analogous to the longitude and latitude on Earth, it's effectively taking the Earth coordinates and mapping them onto the sky. Right ascension and declination, or RA and Dec if you prefer, they've been used in star atlases since the days of the first Astronomer Royal. It's the standard way of plotting the positions of stars in the sky. Why is that not good enough for what we're trying to do here? Well, if you again think about a page of a star atlas like this, the right ascension and declination coordinates are written out, and we can read the coordinates off the map, or we can read the coordinates of a star off a star catalogue, and we can tell what the coordinates of any star are by where it sits relative to the right ascension and declination grid. But if we were to look, for instance, at a star atlas for epoch 1950 and another star atlas epoch 2000, these are not the publication dates. These are the dates at which it has been calculated where to plot the stars in terms of their coordinates. Why does it matter that these epochs are different? Because the apparent positions of the stars in the sky will change. Their coordinates in Norton's 1950 are not the same as the coordinates given in Norton 2000. And that's because RA and Dec are based on the equator of the Earth and the pole of the Earth. But these two things are not fixed in space. The Earth's axis precesses. The position of the Earth's pole will point to a different part of the sky. And therefore, the apparent coordinates of a star, which is based on positions of the Earth, they will keep changing. Second by second, minute by minute, day by day, the right ascension and declination of any star will continue to change because of the motion of the Earth. So having a coordinate system based on the Earth is not a good way of trying to fix where is a star in the sky. So what's the alternative? If you say we're not going to use the Earth as a reference, then you might say, fine, let's decouple from the Earth. Let's take everything relative to the sun. Well, even that isn't accurate enough because the sun is not technically the center of the solar system. The solar system, the sun, is surrounded by a whole load of planets which are orbiting around, and so the position of the sun actually keeps changing. The center of the solar system is shown by that X. In this animation, it's slowing down slightly to show us that as we go into 2027, 2028, the center of the solar system actually falls inside the sun. But at other times, for instance, back in the 2020s, the early 2020s, the sun was actually quite some way away from the center of the solar system. It depends on where Jupiter is. If Jupiter and Saturn are on the same side of the solar system, the sun will counterbalance it on the other side of the center of mass. In 2027, Saturn and Jupiter are spread out in the solar system, and so the center of the solar system is close to the center of the sun. So we tend to think, and we often say, that the planets orbit around the sun, but actually they don't. The planets orbit around the common center of gravity, just like the sun orbits the center of gravity. In astronomy, we call that the barycenter, the center of mass of the solar system. And so the best coordinate system to use is not the Earth, not the sun, but the thing that in principle is not changing in the solar system, and that is the solar system's center of mass, that big X in the sky. And we know where that point is. We can calculate, because we know where the planets are, we can calculate where this barycenter is, and now we want to plot the positions of the stars relative to that particular point in space. So the situation we've got, if we were to imagine let's look out into the sky and just think about parallax. Because of the motion of the Earth around the sun, anything close to us is going to appear to move a lot. Anything a long way away is going to appear to move a small amount. Every star will make a small ellipse in the sky, a big ellipse or a small ellipse. But then if we take into account the fact that the stars themselves are moving, then what we're actually going to see in terms of the motions of all the stars in the sky is that every star is actually going to perform a little corkscrew. Circular because of our motion around the sun, plus some sort of drift, some proper motion of the star itself. And so every star is going to corkscrew because of the dual effects of parallax, elliptical motion, plus motion around the Milky Way. Now, motion around the Milky Way, all the stars will be in orbit, but over a relatively short period of a few years, compared to a few million years, the stars will simply appear to move in small straight lines. So to first approximation, we can say all the stars are going to make this corkscrew. So what we need to do, the only problem for Gaia to sort out is there's 1 billion corkscrews up there, sort them out and separate all of the parallaxes to give us distance from the proper motions, which tells us about the dynamics of the Milky Way. That's quite an ask. The first satellite that tried to do that was Hipparchus back in the 1990s, late 80s, early 90s. Hipparchus, named effectively as a homage to the Greek astronomer Hipparchus. You can see the acronym at the top there, which is a sort of a reverse acronym to make it sound really cool. What Hipparchus did was catalogue the positions of 100,000 stars. 100,000 might seem like a lot, but that's only a tiny fraction of the galaxy. It calculated the positions of the stars to an accuracy of about a milli-arc second, 0.001 arc second, 1,000th of an arc second. So it used an accuracy of a milli-arc second to get the parallax of some stars. Not the most distant ones, because they are so distant, you need a much better accuracy than simply 1 milli-arc second to do that. It went down to about magnitude 12. As many of you know, magnitude 12 isn't that faint. That's the sort of magnitude you can get down to with a good pair of binoculars. Just as a reference, the Hipparchus catalogue was used as the pointing catalogue for the Hubble Space Telescope. In terms of making sure the Hubble was pointing at what it thought it was pointing at, it used the Hipparchus catalogue to make sure it knew where things were supposed to be. 20 years later, along comes Gaia, because it was decided we want to do a better job than Hipparchus. The acronym, forget the acronym, it doesn't matter, because when they first put the acronym for Gaia together, they had a particular idea of how it was going to work. They then changed the idea of how it was going to work, but they liked the name so much they kept the name. So it's still called Gaia, but it no longer stands for that particular thing at the top there. The idea was Gaia will be launched and will improve on the Hipparchus satellite by mapping not 100,000, but by mapping at least 1 billion, if not 2 billion stars. And it will do it not with an accuracy of a milli-arc second. The intended accuracy was 10 micro-arc seconds, or 100 times better, because a micro-arc second is 1 part in 1,000 of a milli-arc second, which is 1 part in 1,000 of an arc second. So the idea is if you have higher precision, then you can decouple the effects of parallax from the effects of proper motion. So you can get the distances of stars much further. You have a much further reach into the Milky Way if you can look at tiny changes, despite the fact that the Earth is still just moving 1 astronomical unit away from the sun. If you have a high enough accuracy, high enough precision, you can determine the parallax of stars at a much greater distance. So you get a much greater reach into the Milky Way. And also Gaia was planned to look at much fainter stars, not a limit of magnitude 12, but now we're talking a limit of magnitude 20, much, much fainter stars. Now it's easy to throw these numbers around and say milli-arc seconds, micro-arc seconds, but none of us have got any sort of gut feeling for what that actually means. So let's have a little analogy to make it clear just what a crazy precision we're talking about here. We're talking about 10 micro-arc seconds. When all the data is analysed, it's intended that the final results will be precise to about 10 micro-arc seconds. That's equivalent to the thickness of a human hair seen at a distance of 1,000 kilometres. So imagine standing in Land's End, looking at somebody in John O'Groats and determining their position to within the width of a human hair. That's the accuracy that Gaia was set to determine the positions of stars. It sounds crazy until you realize it's been done. So, Gaia obviously did this, but we can take a step back and say, well, did we really need Gaia? Can we not do that with the telescopes we already had? Isn't the Hubble Space Telescope a fantastic telescope? Doesn't it have fantastic ability to point and precisely take images? And if not, well, surely we've got the Shimonyi telescope, previously known as the Large Synoptic Survey Telescope. Isn't that capable of surveying billions of stars? Well, if we think about the properties of those two telescopes, the Hubble certainly has precision. The Hubble could determine the position of a star to an accuracy of about a milliarc second, and hence could determine the parallax of quite a few stars. And yes, the Shimonyi telescope is certainly capable of surveying 1 billion stars. That's what it's going to be doing. It'll probably end up surveying 10 billion stars at the end of its survey. But the Shimonyi telescope doesn't have the resolution. It only has something like 100 times worse resolution than the Hubble. And the Hubble does have pretty good resolution, but it's only actually determined the parallax of about 1,000 stars. If you wanted to cover the entire sky, the Shimonyi could actually do that in 10 years. It is going to do that in 10 years over and over and over again. If you wanted the Hubble to actually map out the parallax and proper motion of all the stars in the sky, it can do that. It would take approximately 1,000 to 2,000 years to do that. And therefore it was not considered viable because it's not likely the Hubble will last quite that long. Its gyros are going to fail within the next 10 years probably. So no, some telescopes are great at what they do, but no telescope was considered good enough for the task of determining the parallax and the proper motion of stars in the Milky Way to an accuracy of 10 micro-arc seconds over the next decade or so. So they built Gaia, but how on earth did it achieve that incredible level of precision? Gaia was an ESA mission, the European Space Agency. It involved input from essentially every European country. The French, the German, the Belgians put into the optics. They built the mirrors, the silicon carbide mirrors, which I'll show shortly. The detector was built here in the UK. Hurrah! Yeah, E2V built the detector. And some of the power systems were put together by British Aerospace in Stevenage. So the UK has a significant investment in the Gaia mission. These various things were built in various countries around Europe, and then the final assimilation, the final systems integration was carried out in Toulouse by a company called Astrium. Astrium now is part of the Airbus consortium. So effectively, Gaia is effectively an Airbus, if you like, if you want to think of it that way. It was put together in the late noughties up to about 2012. It was launched in December 2013, and very quickly thereafter placed into a halo orbit around L2 in January 2014. A halo orbit much like the James Webb orbit in the same place. A reminder of L2, let's get rid of the other Lagranges. L2 is that point there, sitting 1 million miles above midnight. Noon, of course, is this side of the Earth, the one facing the sun. Midnight is the side of the Earth facing away from the sun. And 1 million miles above that, 1.5 million kilometers, roughly speaking, is the L2 point. And Gaia was in orbit around L2, much like the James Webb currently is in orbit around L2. The advantage of sitting there is that with a sun shield, you can block all of the light from the sun and the Earth and the moon, and then you get an unobstructed view of the sky on the other side. And throughout the year, you then get to see the whole sky. This is what Gaia looked like when it was being put together by Astrium in Toulouse. They're checking that the sun shield opened up. You can see the size. The sun shield is less complex than the JWST one. The sun shield is about 10 meters in diameter. Notice the solar panels on the underneath to give it the power there. So of course they checked that the sun shield deployed correctly. They tested, retested over and over again to make sure that once it was at L2, it would be performing correctly. So we return to the question, okay, Gaia is sitting there at L2 ready to do its job, but how on earth does it get accuracy that can be measured in the tens of micro arc seconds? We know the bigger the mirror you have, the better the resolution you have. That's why we want bigger mirrors. That's why we want the extremely large telescope, not only to gather more light, but to get greater resolution. But if Gaia has got to get a precision 100 times better than Hubble, surely that means it's got to have a mirror 100 times bigger than Hubble. Are we going to have a mirror that's a kilometer in size? Well, clearly not. We've seen Gaia. It's only a few meters across. So how did it do that? Let's just remind ourselves about mirror sizes. There's the largest telescope in the world at the moment on the Canary Islands. Of course, it's going to be overtaken fairly shortly by the European Extremely Large Telescope there on the right-hand side. The space telescopes are down in the bottom left-hand corner. Let me blow that up so you can see it a little more clearly. Gaia is in the top left there. Gaia is those two rectangles. That seems rather odd for a telescope to have mirrors that are two rectangles rather than Hubble's familiar one circle with a hole in the middle and James Webb set of segments there. So Gaia clearly is no bigger than Hubble and no bigger than James Webb, and yet can achieve phenomenal accuracy of determining the positions of stars. How did it do that without a huge mirror? Well, a combination of really ingenious instrumental hardware and a novel way of working. And that is one of the takeaways that I hope you get from this talk, that Gaia works in a way that you probably didn't appreciate. So let's have a think about the hardware. Firstly, it has a very large detector. The detector is a detector array of about 100 or so CCD chips, CCD sensors, each of which is 9 megapixels, making a total of the best part of a gigapixel. It's about 900 megapixels in total in this CCD array made at E2V in the UK. And although I describe Gaia, and everybody else does, as a space telescope, technically it's 2 space telescopes, because Gaia actually has 2 telescopes looking in different directions. That might seem very odd. It's even more odd when you think about the 2 telescopes looking in different directions, but they put the image on the same chip. That just seems absolutely ridiculous. Why would you have 2 telescopes pointing in different directions? Surely you want 2 different chips to give you 2 sets of images. No, it's looking at stars in different parts of the sky, and it's bringing the image of those stars onto the same detector. Not only is that rather weird, but Gaia doesn't work in anything like the same way as the Hubble Space Telescope or the James Webb Space Telescope, because Gaia spins. And that means the stars drift across the detector continuously. Gaia does not make images. Gaia makes measurements. It wants to know where the stars are. It wants to know how bright the stars are. It wants to know what the colors of the stars are, but it does not make images. If it did, they'd all be blurred anyway, because Gaia is spinning. So let's have a think about what that actually means. Gaia doesn't work the same way as Hubble or James Webb. The critical difference is the way you get data off the chip, which is something I'm sure you've never even thought about before. If you've got a camera, whether it's an astro camera or a digital SLR camera or whatever, you've probably never even thought about, well, the light hits the chip, how does the data get out of the chip and into my SD card or down into my USB bus? So I'm going to talk about the array of CCD shortly, but just a reminder that CCD means charge coupled device, where the emphasis here is on the first word, the charge. When light hits one of these sensors, the light is converted into electric charge. What we need to do is measure how much electric charge is generated, because that tells us how much light hits that particular pixel in that particular CCD. So what matters is how we get the charge out of a CCD into data. It doesn't really matter what that data looks like. Let's just imagine it's a string of binary numbers like this. The way that is done for an imaging system like the Hubble or the James Webb is nothing like how it's done for Gaia. So let's first think about how it's done in the conventional sense of if we've got a CCD and we want to take an image of the sky, how is that normally done? Let's just imagine we've got a patch of sky, doesn't really matter what it looks like. The image, of course, ultimately what we want is just a whole load of numbers, and those numbers are coming from how much charge is resulting from light hitting the chip. So for a standard CCD, it's used in what is sometimes called stare mode. Because what you do is you stare at a patch of sky. In the case of Hubble and James Webb, you make sure the telescope isn't moving, you fix on a particular target, and you stare at the target and expose the CCD for seconds or minutes. We're going to stare at a patch of sky, and as the seconds tick by, photons arrive, the light is converted to electric charge, which builds up in each of the pixels in the image. Once the exposure is complete, then we want to read that out. So the information is shuffled down into a so-called register, which is then read out 1 pixel at a time, and the amount of charge in each of those pixels is read by an electronic circuit, and converted to a digital number. And then the next line comes down, and again, one by one, they shuffle across to read out. It takes about a millisecond to shuffle the line downwards, and it takes about a microsecond to read each pixel as it comes through this register. One by one, each of the lines shuffles down and then shuffles across until the final row of the CCD shuffles down, and then we have a set of numbers where these numbers represent how much charge was read from each pixel. In other words, how much light arrived at each pixel. And as long as we know the order in which all of this data comes out, we can work out what the amount of light was that hit each pixel of the CCD. And the CCD is now empty. We've taken all the charge out of it and converted it into numbers. We're now ready to take another picture. That whole process of reading might take a second or 2 or 3, depending on what system it is we're looking at. So the Hubble might take a deep field that lasts for a day, but then it only takes a few seconds to actually read out all the information, and there's our image ready for us to do something with. Gaia does not do that. Gaia doesn't stare at a patch of sky and then read the data out. Remember, Gaia is spinning, which means the stars are drifting across the CCD. So we can imagine the stars drifting across the field of view, but the really clever thing is you arrange it so the rate at which the stars drift across the CCD is precisely the same as the rate at which you are scanning and shifting all of the information in the CCD. So a star is hitting that particular point, and as the star is drifting, the entire contents of the CCD is shifting down and down and down until the star reaches the edge of the CCD, at which point it's read out, and at that point it says there's a star. It makes a note of the time. It has an atomic clock on board, so it knows exactly when that star light has arrived, or at least arrived and been read out. And it does that for, of course, more than one star. I've shown here 3 blobs. A star will probably not be just 1 pixel, but in principle, it's what I've said. The stars are drifting across, but they are drifting at exactly the same speed that the CCD is shuffling down, which means the CCD effectively is tracking the star. And then when the stars reach the end, the information is read out. Let's return to this crazy idea of, yeah, all very well, but why on earth have we got 2 telescopes? And why are those 2 telescopes sending stars to the same detector? That seems crazy. 2 telescopes, but 1 detector. There is a precedent for this idea, which you actually probably have heard about. And that's how sextants work. And I'm sure you're all familiar with this because sextants are used for navigation. And I'm sure you all have one in the boot of your car in case the GPS fails. Yeah? Yeah, okay. So a sextant works by having mirrors, a couple of mirrors, and you are eyeballing the horizon through that little telescope. So there's your detector looking at the horizon. And you want to know where a star is in the sky. It might actually be the sun, but let's assume it's a star. The star might be way up there above the horizon. You don't want to look at the horizon and look at the star, and look at the horizon and look at the star to try and work out where the star is. You use mirrors to reflect the starlight such that, as far as your eye is concerned, the star appears to be on the horizon. In other words, you're reflecting light to bring the star down to the horizon. The star is up there, the horizon is down here, but as far as your detector is concerned, the back of your eye, they seem to be in the same place. For a sextant, that's the angle that matters. Once you know that angle, you can use that to work out your latitude. That doesn't really matter in this case. What matters is the sextant uses mirrors such that two objects at two different parts of sky appear to be on the same detector. In this case, the human eye. In the case of Gaia, the same CCD set of chippery. So that means you don't have to go there and there and there and there. The light effectively comes to the same detector. That's what a naked Gaia looks like. There's the primary mirror of telescope 1 on the left and the primary mirror of telescope 2 on the right. Each mirror is about 1.5 meters by 0.5 meters. And that's where you can see it being put together by the Astrium technicians, where they seem to be fitting telescope mirror number 2. These mirrors are silicon carbide mirrors made in France, Germany, Belgium. Let's have a look at the detector made by E2V in the UK. It's a whole load of so-called astrometric chips. Each of these chips is the size indicated there, and 9 million pixels, each of which is that size. They're rectangular because it's much more important to get high resolution in the horizontal sense than it is the vertical sense. And they're the same shape, effectively, as the mirrors themselves. These so-called astrometrics CCDs are responsible for the timing of when a star is transiting across a CCD. It's a bit like saying this is a really high-tech transit telescope because it's not imaging the stars as they go by, it's timing when every star appears at a certain point within the detector. In addition to astrometrics, there's a couple of presets of CCDs. These are responsible for making sure the system on board knows whether the star is in telescope 1's field of view or telescope 2's field of view. So we have to know which is which, so we know which part of the sky we're looking at, but that's dealt with by these so-called mappers. After that, all the stars drift across the astrometrics CCDs. Then they drift across a couple of other sets of chips after going through a little prism, so that we can measure how bright is this star in the blue part of the spectrum, how bright is this star in the red part of the spectrum. And some of the stars will then go through a spectroscope to have their full spectrum actually recorded. In addition to those chips, there's also a small number of other chips, WF, their wavefront sensors, to actually make sure everything is in focus correctly. And the BAM chips are there to make sure that the two arms of the telescope are exactly where we think they are. If these two arms move in any sense, if the two mirrors are not absolutely stable so that we know which way those two telescopes are pointing, then all of accuracy of Gaia disappears. It's absolutely critical we know what that angle is. We know what it should be. The temperature of Gaia is stabilized to better than 1/1000th of a degree centigrade to make sure that there's no motion there, no thermal motion of any of the mirrors that could possibly change that angle. The stars are drifting in the horizontal sense across the detector here from right to left as we look at them. And it takes about 4 seconds for a star to cross one of these chips. So in other words, it takes about a minute to cross the entire detector. So the animation I'm going to show you is not quite real time. So let's have a look at the operation of Gaia. This is an ESA video showing the two telescopes in Gaia looking at two chunks of sky, color-coded magenta and cyan, just so we can tell them apart. Let's have a look at the light entering the first telescope. That hits the main mirror and then bounces off loads of secondary mirrors before it finally arrives at the detector. So we have a whole load of stars hitting the array, and we know that they came from telescope number 1 because they hit this particular sky mapper on the right. Then what happens with telescope 2? It has its own optical path but ends up on the same detector, except that now we know they're from telescope 2 because they hit the second sky mapper. And with time, all of these stars are drifting across the field of view. As a star drifts across a CCD, it is tracked until it gets to the end, and the time it arrives at that point is stamped to within a microsecond. Then it goes across the next CCD, and the time it arrives at that point is again noted, as well as the brightness of the star. For each CCD, it makes a note of the brightness of the star and the time it took to arrive. And then it notes how blue was the star, how red was the star, and for some of the stars, let's also take a spectrum of the star. So it has multiple time points to note when the star arrived at that particular point in the detector, and it has multiple opportunities to measure the brightness of the star. So we've got a lot of averaging that we can do to get much higher precision than any single measurement. Any star is measured multiple times, and as Gaia spins, that star comes round again, and it takes another set of measurements. And as it spins, that star comes round again, and it takes another set of measurements. So Gaia is all about multiple measurements of the same star to improve the accuracy. This cartoon gives us an idea of what's going on. Loads of stars are going across the detector at any given time, and information is being read out from CCDs all over the array. The difference between this cartoon and reality is that the cartoon shows a couple of dozen stars. In fact, there might be 500,000 stars on the array at any given time, and there will be thousands of stars read out each and every second in terms of the date stamp, the time stamp to within a microsecond, and the brightness of the star, and the color of the star, and the spectrum of the star. Thousands of readings per second, 24/7, for 10 years. There's no need to stop, it just keeps going and keeps going, like the Ever Ready Bunny. This is what it looks like. Gaia is actually spinning once every 6 hours, not as fast as that animation would imply, but faster than the Earth. And it also precesses to make sure it covers the entire sky. So Gaia is effectively mapping out a ribbon of sky, but that ribbon of sky will sweep across the whole sky over a period of weeks and months and ultimately years. And it will cover some parts of the sky more than once. The colors here represent how many times that patch of sky has been covered by Gaia sweeping out. So you can see it doesn't necessarily cover every point in the sky at the same period, at the same cadence. In some cases, it's mapped a star many times. In some cases, it's mapped a star slightly less number of times, but in all cases, it gets the required precision. So what data was actually acquired during the 10 years of life of Gaia? The original mission ran from 2014 until about 2019, but it was working so well, they figured they'd let it run longer, and it turned out to have a lifetime of about 10.5 years before they no longer had the ability to control its spin rate precisely. Data was released from the original data set. It takes a while to figure out what the data actually is, though. Remember, as well as brightness, Gaia is taking billions, if not trillions, of measurements of the time that this star crossed this CCD and the time that this star crossed this CCD. And it's doing that for stars visible in that telescope and stars visible in that telescope, and it's doing that simultaneously. So it's got a very good idea of where this star is relative to that star. And because Gaia is spinning, it can do that again for different patches of sky, and it can effectively do that for the entire sky. But the raw data of Gaia is lots and lots of timings, which then the guys on the ground have to take and say, right, we're going to take these billions of time measurements and we're going to figure out where those 1 billion stars are that's consistent with the fact that we've got this timing, this timing, this timing, this timing, etc. It involves an awful lot of commutation, which means the data wasn't released immediately. They started to map out the stars. The first data release was back in 2016. 7 data releases. Did they number them 1 to 7? No. They numbered them 1, 2, E, 3, F, 4, 5. The first data release covered the first year's data, the red rectangle in the top left there. The first 1 year of Gaia data was analysed to try and generate a map of the sky, and they produced a catalogue of some millions of stars. Data release 2, 2 years later, they took 2 years of data and produced a catalogue not of millions of stars, but of literally billions of stars. So now we've got some really good data, not quite at the precision we want, but some pretty good data for billions of stars that were mapped out in the first 2 years of the mission. Scientists were getting pretty antsy waiting for data release 3, which was going to be much higher precision. So they decided to have an early data release, E, in which they took 3 years worth of data to improve the precision with which they have now mapped out the various stars in the sky. Data release 3 eventually came along in 2022, where in addition to having relatively high precision of billions of stars in terms of their position and hence the parallax and hence the distance and the proper motion of how these stars were moving, they also produced a whole load of data on millions of variable stars that had changed their brightness over these 3 years, as well as millions of galaxies, hundreds of millions of spectra of stars, and almost by accident, hundreds of thousands of solar system objects, some of which we knew about, some of which we didn't. The idea of looking at lots of galaxies, that wasn't Gaia's job. Its job was to look at the stars. But along the way, you'll also get blobs of light in the background. The very distant galaxies will appear to be essentially stellar. They're so far away, they are just points of light, so-called quasars. Very distant galaxies with a bright nucleus that looks effectively stellar. These are really useful because these galaxies, not necessarily millions of them, but a subset of them that are really far away. If you think about it, if the object is 1 billion light years away, then the motion of the Earth around the Sun is effectively going to make no difference. The parallax of that object is effectively 0 because it is such a great distance away. So the parallax is 0, and over a period of a few years, the galaxy is not going to move from that point in the sky. So we have 0 proper motion and 0 parallax. These are effectively fixed points in the sky. This is exactly what Gaia wanted. We need to know the positions of stars relative to a fixed grid. We now have a fixed grid because it has seen hundreds, if not thousands, of quasars at a far enough distance that they can be considered to be unmoving. So that is a very useful calibration for Gaia. Before data release 4 was another so-called focused product release, which is a bit of an odd name, but it took data from the first 5 years. You can see the red bar there. We've taken data from 5 years and started to do analysis on particular things in the data set, not necessarily looking at all of the billion stars in the data set. But one of the things they did is to say some parts of the sky are really crowded. Sometimes it's very easy to work out the positions of stars when the stars are nicely separated. But there are some parts of the sky, like for instance, the center of the galaxy or the Omega Centauri globular cluster. These are really crowded. So what they decided to do was to take a breather and say, can we really get the sort of resolution we want from an object like Omega Centauri? They used that as a touchstone to see if they could refine their analysis to see what was going on. Remember, globular clusters can be very dense. Omega Centauri is one of the densest globular clusters, if not the densest globular cluster around. Even the Hubble Space Telescope has difficulty figuring out what's going on anywhere near the center. Yes, it can see individual stars away from the center, but it gets really, really crowded. They refined the analysis they were doing to try and pick out individual stars' positions and motions, And Gaia found more stars than Hubble can see in the Omega Centauri cluster. Gaia found 500,000 more stars than Hubble could see in the Omega Centauri cluster. So they've now refined their analysis using that as a touchstone. So they now figure, right, we now should be able to start looking at the center of the galaxy where things are getting really crowded, and maybe we'll be able to pull out even more than we thought from that particular part of the data set. Data release 4, which is going to be coming out this year, it was originally scheduled for sort of early-ish this year. It's more likely to be late this year, but data release 4 will be coming along in 2026, and that should include the analysis that they've been refining by looking at, for instance, the Omega Centauri globular cluster. Eventually, way down the line, data release 5 will include the entire data set. All 10 years will be used to refine, to get the maximum accuracy, the maximum precision of all of these positions and parallaxes and distances and proper motions. But that is, of course, some way down the line, something like 2030. So we can look forward to data release 4 fairly soon, in a few months. Data release 5, not for a few years. Let's remind ourselves what the Milky Way actually looks like. There's the Milky Way with its spiral arms labeled. We're in the Orion arm, what used to be called the Orion spur, and that's us there. The region covered by Hipparchus was everything inside that yellow circle. Tiny. 100,000 stars is a tiny fraction of the Milky Way. Gaia's data release 2 allowed us to see further. Everything inside that green circle has been covered by Gaia data release 2 in 2018. 4 years later, Gaia data release 3 expanded that green circle into a much greater coverage of the Milky Way. Now we are able to look at stars within the green circle. So our reach has now gone to something like 10 kiloparsecs, or 30,000 light years. Remember, 3 light years would have a parallax of 1 second. So 30,000 light years has got an absolutely tiny parallax of just 100 microarc seconds or so. That's not an image, that's just a map showing a brightness according to how many stars Gaia found in a particular patch of sky. And not surprisingly, it sort of maps out how we see the Milky Way. But what do we actually learn when we start to look at all of the Gaia data? Earlier, I showed a Hertzsprung-Russell diagram, luminosity versus color, and that was a schematic. This is the actual Hertzsprung-Russell diagram of millions of stars. Each dot is an actual star that's had its color and luminosity recorded. And the colors here in the middle simply say how many black dots are overlapping to give us an idea of what's going on in these regions. So this is the actual Hertzsprung-Russell diagram of this half of the Milky Way, if you want to think of it that way. Rather than schematically saying that's what we think it looks like, we now know what it looks like. And this allows astrophysicists to get a better handle on the stellar population of our Milky Way. Accidentally, it also found a few other things. Rather surprisingly, it found a whole load of stars that are very much like our sun, but they appear to be orbiting a neutron star. This was rather unexpected. How can you have a sun like ours orbiting a neutron star? A neutron star is the result of a supernova explosion. How can you possibly survive that if you're right next door to it? But various stars have been mapped out after you've accounted for parallax due to the Earth's motion, after you've accounted for the motion of the stars seem to be orbiting something we can't see. It's too massive to be a planet, not massive enough to be a black hole. We think these are neutron stars. So lots of people are getting their teeth into this data to try and understand why are we finding dozens of examples of stars that have survived a supernova explosion. This is possibly only a 1 in a million event, and yet Gaia has found dozens of them because it's been looking at so many star candidates. Looking at where the stars are in the Milky Way, we've come to the conclusion that the Milky Way is warped. If it's warped, well, it's warped because presumably we've had interactions with other satellite galaxies which have warped our galaxy. We've seen that in other galaxies. If you look very closely at the dust lane in the middle of this galaxy, it is not quite lined up with the galaxy itself. This galaxy is warped. We suspected that might be the case for the Milky Way. Now we know it is. And if we look at star motions, here we have an exaggerated video of how the stars are moving through the sky. If we look at not where they are, but how they are moving, we find a lot of stars are doing what we would expect them to do, like us, orbiting around the center of the Milky Way. But some of them are doing really odd things. Sometimes the motions of these stars indicate that the stars are going backwards. In some cases, the stars aren't moving in nice big circles, they are moving in really exaggerated ellipses. This would imply something dramatic happened that made those stars move the way they have been doing. We came to the conclusion that the Milky Way must be the result of lots of galaxy mergers that have happened in the past. Over billions of years, small galaxies have merged together to give us the Milky Way that we know and love today. We always suspected that was the case. Now we know that's the case because Gaia data is giving us the positions of stars that tells us there have been galaxy mergers over billions of years, almost since the Big Bang itself. Perhaps as early as 1 billion years after the Big Bang, we have evidence that galaxies have started to merge and the Milky Way has grown over this time. I'm not going to talk about all the details of all of these galaxies. One of them was called Enceladus. We think that 10 billion years ago, the Enceladus galaxy merged with the Milky Way. Some of the globular clusters that we see today appear to be odd. And we think that's because they came from another galaxy. They came from Enceladus. Enceladus brought those globular clusters with it and then merged with the Milky Way. And now we have a population of some globular clusters which we were born with and some globular clusters that other galaxies have brought to us. I'll say something about the Sagittarius dwarf galaxy in just a moment. This is simply a hypothetical what might happen when another galaxy merges with the Milky Way. If we think of the original Milky Way being blue and a little dwarf galaxy hitting us, you can see that the dwarf galaxy in red is disrupted and the stars are scattered. But even though tidal effects between the two galaxies tends to rip things apart, even after a little while, it's clear that the red stars haven't been distributed uniformly around the Milky Way. They're still in particular areas. And if we can identify those in the Gaia catalogue, we can say these stars seem to be similar age, similar chemical composition, and they seem to be in the same patch of sky. There's evidence that they are the result of a merger with an earlier galaxy. In the case of the Sagittarius dwarf galaxy, we have evidence that the dwarf galaxy clipped the Milky Way some 6 billion years ago, didn't completely disintegrate, came back and clipped us again 2 billion years ago, and then continued on its way and clipped us a third time 1 billion years ago. And in the process, produced this breadcrumb trail, this star stream, or if you prefer, tidal tail of an evidence that we have had a galaxy orbiting around us for the last few billion years. What I find particularly interesting is we know that whenever galaxies interact with each other, the perturbation, the tidal effects of one galaxy on the other often produces new star formation. And one of these interactions of the Sagittarius dwarf galaxy with us was 6 billion years ago. Just about the time when the sun was born. So it is quite possible, very difficult to prove, but it's quite possible that we are here because the sun was born, because the Sagittarius dwarf galaxy clipped us and produced a whole load of new stars, and maybe our sun was one of those stars. So maybe we owe our existence to the fact that the Sagittarius dwarf galaxy came and gave us a clip 6 billion years ago. Star streams are everywhere. Here's a particular example. I'll invert it to make it even more obvious. There's the higher contrast version. These ideas of satellite galaxies producing streams as they interact with each other, they're actually everywhere the more we look. M63, it looks like just a static galaxy, but if you invert it and bump up the contrast, it is obvious that there are star streams everywhere, indicating that this galaxy has interacted with others in the past as well. The more you look, the more you see. So because we've seen this in other galaxies, in that sense, it's not a surprise to know that yes, we have merged with other galaxies in the past. But rather than just being an assumption, we now have the data that actually backs up the fact that yes, we have interacted with the best part of a dozen smaller galaxies in the past. There's another example of Fornax, where there's obviously a lot of stars that are the result of the interaction of these galaxies. It's not only a question of the history. I'm not going to go through the history of all of these other interactions, but not only do we know that this set of interactions probably took place in the past. Notice that the Sagittarius dwarf galaxy hasn't been finished off here. It's because that interaction is still going on. To the best of our knowledge, in the future, that interaction between us and the Sagittarius dwarf galaxy will continue. We see stars out there that are part of this remnant galaxy, and they'll be back. But as much as anything, the most important thing here is that we know that there are two things going to happen in the not so distant future. Gaia has looked very closely at all of the stars in the Large Magellanic Cloud, and it has come to the conclusion that we now know how the Large Magellanic Cloud is moving, and we know it's going to collide with us between 2 and 3 billion years from now. And this is the one that I presume everybody knows about. We are going to collide with the Andromeda Galaxy. Despite being 2.5 million light years away, it is still possible for Gaia to see a small shift as the Earth moves around the Sun by 1 astronomical unit, even though the stars in the Andromeda Galaxy are thousands, if not hundreds of thousands of times further away than our local stars in our galaxy. Gaia has determined that M31, it wasn't quite convincing, but it looks even more likely now that the collision with M31 is not going to be a glancing blow. There is now evidence that the collision is going to be head-on rather than just a glancing blow. But we still need more accuracy on that. Maybe that will come with data release 4 or possibly data release 5. So I've sort of had my time, so let me finish with an epilogue. Gaia finished its data acquisition in January of last year, so it basically died about a year or so ago. In March of 2025, it was placed in a retirement orbit. Sounds so much better than a graveyard orbit, doesn't it? Basically, that means you just nudge it away from L2, and then it goes into orbit around the Sun. Remember, for the James Webb, we're trying frantically to make sure James Webb doesn't go beyond L2, because once it does, it's effectively lost. In the case of Gaia, it was deliberately pushed beyond L2 to get it out of the way of anything else that wants to use L2. As it drifted away from L2, some amateurs managed to get a picture of it. That S is Gaia moving away from the L2 point, light reflecting off its sun shield. It might be back in a little while, another 14 years, it might return to Earth, not very close. It's never going to come back to Earth, it's never going to come back to L2. It might be close enough to photograph again in 14 years' time. Just before it powered down, they instructed it to send one last data set back to the mission controllers, and the data set it sent back was this one. Look at the colors. They sent it dummy data so that when the dummy data came back, it says, bye. Is Gaia going to be replaced with anything else? There's thoughts that it would be really good to have a Gaia that works in the infrared. Because remember, a lot of the Milky Way is rather dusty. It's very difficult to see through the dust in the visible part of the spectrum. If we had an infrared version of Gaia, it would be able to see even further into the dusty center of the Milky Way. There are thoughts about doing that, but if there is an infrared Gaia, it wouldn't be until 2045 or possibly 2050. And that's assuming that they get funding for it in the meantime. There will be other infrared telescopes going up. The Nancy Grace Roman telescope will be launched this year or possibly next year. The Nancy Grace Roman will work in the infrared and in principle will be able to see into regions that Gaia finds rather difficult because of the dust. Bear in mind that the Nancy Grace Roman image field of view, as shown here, is absolutely enormous. That is the Hubble Space Telescope field of view. The Nancy Grace Roman imaging will be at the same resolution. But if you look at the pillars of creation there, imagine images with the same resolution of Hubble, but the image is 100 times bigger. Nancy Grace Roman is going to be a fantastic telescope. It will not replace Gaia, but it might be able to augment some of the data, especially in the dustier regions of the Milky Way. So Gaia has produced shed loads of data. Data release 4, it is said, will be approximately 500 terabytes of data. What do you do with all that data? Well, you get some very clever people to think about what it all means and how it's going to be interpreted. You get a lot of clever people, perhaps assisted by a few AI tools to help them along the way, because it's an awful lot of data. And if you look at that data and you figure out where the stars are, how distant they are, what the three-dimensional structure is, how those stars are moving, then you can get information about the Milky Way dynamics and the Milky Way evolution and the Milky Way history of mergers and possibly the future of mergers with other galaxies. But remember, it's not just about how stars are moving, it's also about star colors, star spectra, from which we can get chemical compositions and mass and age and other factors. So all of this data that's buried in the data catalogues of Gaia also improve our understanding of the mechanics of stellar evolution. So we'll understand more about the Milky Way, and we'll understand more about the stars within the Milky Way. As a sort of a spin-off, we'll also get some information about neutron stars. That was rather unexpected. Gaia has also found a black hole, which is one of the biggest black holes, other than the one at the center. It also has found various solar system objects, and it's also discovered a few exoplanets by accident as well, because of the motion of the stars indicating a planet is going around. Data release 5, when it eventually comes in 2030, will have so much precise data about all the stars in the Milky Way, hopefully that'll allow us to get more information about dark matter and dark energy within the Milky Way, how it's distributed and possibly how it's changing. Two words that have described Gaia in the past: obscurity and ubiquity. Obscurity because it's a lot less known to most people in the public compared to its brethren like the Hubble Space Telescope and the James Webb Space Telescope, which produce beautiful images. Gaia doesn't, and so it doesn't get the headlines, it doesn't get the publicity. But ubiquity, because Gaia is producing data which is going to be used by every ground-based telescope. It's produced data which is going to be used by every space telescope. It's generated data which is going to be used by thousands of astrophysics research projects in the next 10, 20, 30 years. Gaia's data is Gaia's legacy. Thank you all very much.